Example, prove that the trace of or trace function is a linear function on the space of all n cross n matrices over the filled F. Solution. Now before starting its solution, first of all we will see what is the trace of any matrix. So what I am writing in the beginning, it is not part of this question. So this is just for your understanding what is the trace of any function. See, actually we are finding trace of any matrix. So suppose we have any matrix A as A, B, C, D, E, F, G, H, K. So if this is the matrix, then trace of A is nothing but the sum of all diagonals value, that is the sum of A plus E plus K, or we can say that trace of any matrix is nothing but sum of all ij where I is equal to j, that is A11, A22, A33. If this is in the term of A11, A12, A13, A21, A22, A23, A31, A32, A33, then trace of this matrix is nothing but summation of Aij where I is equal to j. That is the sum of all diagonal values is nothing but the trace of any elements. So it is always necessary that we can find trace of only square matrix, not non-square matrix. So this is the definition of trace. Now it is given in the question that we have to prove that the trace of any function is always a linear function. Now we will start proof of this question. So solution, we are starting from here. So let n be a positive integer, n be any positive integer, and f be a field. Also let v of f be the vector space of all n cross n matrix over F if we are assuming that A is any matrix Aij of order n cross n which is belongs to V of F, then the trace of this matrix is given by A is defined as I already told you, trace is defined as the sum of all diagonal value. So here trace of A is defined by the scalar. What is that scalar? We are denoting trace as TRA. So this is the shortcut to write trace. TR is nothing but trace. Trace of A is nothing but A11, A22 plus up to ANN. So we can say that trace is nothing but I is equal to 1 to n I. So we have trace when our I and j are equal, that is the trace when we are adding all the diagonal values. So now we will define a functional. Define a functional. So in the question functional is not defined, but in some question they may define function, then you have to only calculate, you have to only see that whether it is linear functional or not. If the statement is given, then you have to define what is trace, what is your domain, what is your codomain. So here it is not defined, so we are defining define a functional f. So it is given that it is a linear functional on space of all matrices. We know that this can be written as v of f, and this is the trace function. So trace function is, we are writing this will be element of f only. So we are defining f is a mapping from v of f to f by f of a is equal to trace of a, that is sum of all diagonal elements, that is i's from 1 to n, for a is equal to aij n cross n, that is a is nothing but our matrix. Now we have to prove that f is a linear functional, that is f of alpha a plus beta b is equal to alpha times f of a plus beta times f of b. So if you once write what you have to prove, then it will easy to solve any question. So here we have element of our domain are matrices, so we are writing alpha a plus beta b. So it is easy now for us to prove this question. To prove this, let a comma b, that is a and b are any two matrix of our vector space, we be arbitrary, and alpha and beta are any two scalar. So we can write that A is nothing but any matrix. Suppose we are giving name as Aij, all n cross matrix of order n cross n, and B is another matrix having entry Bij, which is also square matrix of order n cross n. Now if I have to find trace of this A, then it is nothing but summation I is from 1 to n aii, and this is nothing but trace of B, summation I is equal to 1 to n all bii. Now we have to calculate alpha a plus beta b. We have to calculate f of alpha a plus beta b, but before doing that, first of all we will calculate this. So alpha a is nothing but I is equal to, or we can say a is nothing but alpha matrix aij, and beta is nothing but beta matrix bij. Here this matrix A has order n cross n. Similarly matrix B also have order n cross n, so we can add these two matrices. Or before that, we know that scalar multiplication of vector can be written. That means if we have any element common in entire matrix, then we can take it outside. So if we have alpha into matrix aij, then I can write this as alpha aij plus beta bij. Now these are two separate matrices, and I can add these two matrices. So this become my new matrix alpha aij beta bij. So from these two matrices I am getting one new matrix, which is my alpha aij plus beta bij. Now f of, or before doing this, so f of alpha a plus beta b, here we have defined this as trace of matrix alpha a plus beta b. So trace of this is nothing but summation I is equal to 1 to n, alpha remains as it is, and for matrix A we have entries aii, so this become aii plus beta bii. So this is the trace of this matrix. Now I can separate this, so I can write summation I is 1 to n alpha ai plus summation I is equal to 1 to n beta bii. Now as alpha is any scalar, so I can take it outside from summation, so this become alpha into summation I is equal to 1 to n aii plus beta summation I is equal to 1 to n bii. So this remain alpha, but if we see or this value, then we can say that this is nothing but trace of matrix A and this is nothing but trace of matrix B. So from here we can say that this is nothing but alpha times f of A plus beta times f of B. That is f of alpha A plus beta B is equal to this. Therefore we can say that f is linear functional, or we have proved that trace function is linear functional. So this is the second question of this linear functional topic. So here we have proved that the trace of all linear trace function is always a linear functional on the space of all n cross n matrix over the field F.